The next speaker in the session will be presented by Sanchez-Stern, who used to be postdoc at the University of Massachusetts Annex, and right now he's doing some cool work at the startup. But the paper is going to be on the QED Cartographer, automating formal verification using reward-free reinforcement learning.
Hey, I've heard all the info. This is a proof synthesis tool, and the subtitle is a lot of parts, right? Automating formal verification with reward-free reinforcement learning. So I'm going to kind of go through some of that, in detail. So formal verification, for those of you who don't know, is just writing proofs about programs. It's really great because it's more reliable than testing. You can say things about all inputs to a program as opposed to just some of the inputs or particular inputs. But it's really labor intensive and it requires specialized expertise. So automating it is super useful with these proof synthesis tools, saves you a lot of labor. And the number of tools that are automating program verification, proof synthesis tools, have exploded in the last 10 years. Now, generally, the way these tools work is they've got these three components. There's a predictor, which looks at particular proof states and tries to give you a next action to take. There's a search that takes these candidate actions and builds up a tree searching the space of proofs. And there's the theorem prover, which does all the number crunching and tells you when you finish the proof. But the problem with this is that even for seemingly simple propositions, proofs can be an arbitrary length. So the search tree that you're searching actually is totally unbounded. And there are some techniques we can use to help us prune that search tree. We can stop if we see the same state twice, or maybe prune off multiple ways of solving the same subgoal. But ultimately, it's pretty hard to search a space if you don't know how close you are in any sense to where you're trying to get to. So we can search a lot more efficiently if we can evaluate proof states. If we can look at proof states that are easy and say, keep going down this path, you're almost there. We can look at other proof states and say, maybe this will help you, maybe it won't. And we can look at some that are just a total dead end and say, you need to backtrack here, this is not helpful. So if you do this, you can build a more intelligent tree that's based on something more like a star, and you can find proofs faster and find shorter proofs. And that's what we do with QED Cartographer, where we find 26% shorter proofs and 27% fewer steps. Now, this is then the same search without state scoring. So we're keeping the predictor of a prior tool and the same theorem prover, and we're just improving that middle component, the search. So the next part of that title is reward-free reinforcement learning. And when I talk about reinforcement learning here, I'm specifically talking about V-learning, which is a strategy for figuring out the value of states in a state space. So for most of this talk, I'm going to talk about V-learning in general, sort of how it works in theory, what its limitations are in the proof space, and then how we can adapt it to work really well with proofs. So in classic V-learning, you've got some states, you've got some actions, maybe A, B, and C you can take, and actions can give you rewards and lead you to new states. And what you want to figure out is how good is any particular state, and you do that by looking at the maximum across possible actions of the rewards plus the values of the states they go to. And because we care about searching space efficiently and not just searching it at all, we also have this gamma term, which is the time discount. So that says that finding sooner rewards is better than finding later rewards. So we can generalize this equation a little bit from these particular states here to the Bellman v-value equation, which just, like I said, max across actions, reward of that action in that state, plus gamma times the value of that next state. Now, this is sort of a closed form thing, but in practice, we don't solve it for the entire search space. That would be more computationally expensive than just searching the entire space. But instead, we do iterative updates. So we have our agent kind of explore the space, get some rewards, and use that to update what we think the values of these states are. But to do that, we need rewards, right? And the problem with the proof space is that there's only one meaningful objective, and that's finishing the proof, getting QED. So we could give that a reward, but we'd still have all these other transitions that don't have rewards. And so it's really hard for our agent to learn to navigate this space with no signal for most of the time. So to solve this sparse reward problem, we're going to look a little bit beyond this abstraction we've been using so far, where we have just states and actions that lead to new states. Because states and proofs actually have a little bit more structure. Every state is built up of multiple goals, and actions apply to a particular goal at any given time. Each action can generate multiple new goals, or you could have an action that solves a particular subgoal and leaves you in a state with just the rest of those goals. So you have to solve all your goals to finish your proof, but you can sort of solve them one at a time. So at this point, you might think, great, we've got this mini success criteria. We can solve particular subgoals. So if we just reward that, then we solve the sparse reward problem. Unfortunately, adding extra rewards that aren't actually the thing you're searching for can lead to really bad behavior. So for example, let's say you're trying to prove for all x, this p of x, and your agent decides to do induction. So far, so good. We have a base case and an inductive case, and base cases are generally pretty easy to prove. So we're going to be able to prove that base case and get a reward. But then your agent might decide, let's do induction again. And you get about the same base case and about the same inductive case and another reward. And again, and you can keep doing this to have an agent that gets a lot of rewards, feels really good about itself, but it hasn't actually made any progress. So that's not what you want. And that's why our strategy is reward-free, because it doesn't have this problem. So what we need to find here is a new update equation that accounts for the branching structure of proofs without adding these intermediary rewards. And to do that, let's look at sort of a simplified scenario where we have a few actions that lead to this path of states, and we've got this completed state at the end, and we're just going to assume it has the value 1 to start. Now we can run our equation. We know there are no other rewards here. So we're doing 0 plus the maximum across actions times gamma. So the value of state 4 is just going to be gamma. We can do the same thing with state 3, 0 plus the maximum of gamma times the next state. So now we've got gamma squared. And we can keep doing this on and on for state 2 and state 1. And what we notice is that for all of these states, their value ends up being gamma to the power of the number of steps they have left before they get to this final reward. So now, how do we take that and generalize it to the case where we're producing two different goals? Well, if we need m steps to complete one goal and n steps to complete the other, then we know to complete our thing before we branch, we just need m plus n plus 1 steps, right? We need to solve both those subgoals, and we need to take one step to branch them. Now, if you plug this through the power math in that equation, you'll find this means that we need to define the value of our first state. We need to multiply together the values of the two substates, and then multiply them by gamma. So that's our update equation for branch structured proofs. We, like before, are taking the max across all actions, but then we're taking all the different states we generate from that action, multiplying all their values together, and then multiplying it by gamma. You'll notice here, obviously, we don't have that reward term that we had in the Bellman v-value equation, and we don't have to actually set our final value to 1 either. And that's because if you look at a state with a goal, and you take an action that produces no goals, then plugging this through our equation, we're multiplying together all the resulting goals. Since there are none of them, that's taking the product of an empty list, which is just the multiplicative identity 1. So we get gamma for the value of that state right before we finish. And that's exactly the same value we got when we set the final state to 1. So that's the basics of QED Cartographer. We found in our experiments that it produces 26% shorter proofs and 27% fewer steps. We found this by running it on CockGym, this large benchmark of Cock projects, now named Rock, I think. That's 124 Rock projects. And as our baseline, we used Proof 9001. That's what QED Cartographer is based on. We updated the code a little bit. So the difference between our tool and the baseline is just that state scoring and the search. And the baseline is using a variant of depth first search that just gives you a little extra fuel when you solve subgoals. We find indeed that it's 27% faster than that baseline. takes fewer steps to find your proofs, and that it produces 26% shorter proofs. Now, shorter proofs are nice because they're generally more readable, they're more maintainable, and they're less expensive to run the proof checker at any given time. Now, this might not be true depending on the tactics you use, but that's sort of something we can work out in future work. We also find that we prove slightly more theorems than Provebot was able to do on its own, and a very different set of theorems. So combining them, we can do much more. And we think that we could prove even more as an individual tool, but the A-star part of the search isn't as well optimized as the learning of the state scoring function. So that's QED Cartographer, automating formal verification with reward-free reinforcement learning. It uses a new v-value equation that's specified to branching goal structure and might actually be useful in all sorts of branching problems like program synthesis. And it makes producing verified correct code easier and faster. And you can find the preprint at my website at alexsanchez-stern.com. Thanks.